All right, so we're going to talk today about biogeochemistry in ocean general circulation model. Well, this is a vast subject. You know, we could spend a week talking about that. So the way I want to do that is show you what I do every day, pretty much, more than give you, what you should learn or anything. I'll just show you what we do. And I like to start with a quote because just to put everything, my vision of what models should be. And I'm just going to say models, they're there to understand, predict, provide an essential mean of something which is really complicated. So this is what models are for. And behind that, each model should go with the questions. And you'll see that's the take-home message. I'll give it now, I'll give it again. You don't build a model just to build a model. You need to have a question, something specific to address, and you will build a model which fits the purposes. You're not going to go with a model that is there because a supervisor is using it. You take that model and you do stuff with it. You need a question in the back, and that's really important. Why we do it? Because while we love to go at sea and measure stuff, we can't measure everything everywhere. It's just impossible. Even if you give me a lot of money, it's not going to happen. So we need models to help us understand how the system works. And also because the physics is a big part of the story. I know some people hate physics, some people love the physics. Well, when we do biogeochemistry, we can't live without the physics. It's a big part of the signal. And you see here, this is just a few examples. This is STASI, this is all. You see there's a lot of physical structure. The same here, this is just a section. This is all models, sorry. This is just a translate out of currents. You can see here, this is chlorophyll and nutrients. You can see there's a lot of physical structure, internal waves bumping around. It's complicated. The same here, this is just a different cross-section along the Great Barrier Reef shelf, or East Coast of Australia shelf. You can see it. So this is depth, latitude, and longitude here. It's just looking at a section. You can see there's a lot of fine-scale structure. It's a mix of biology and a mix of physics. So we need physics, and to do physics, we need models. As I said, it's a vast subject. There's like millions, not millions, but hundreds of different models to choose from, either from the hydrodynamic or from the BGC. So this is just, with a free example. You can go from the simple NPZD that you guys saw probably 2 days ago to a really high core, complicated models. So you can even go to the one I'm using where we have corals, for example. We have like the interaction of those entirely with symbiotes in the corals. We have seagrass, microalgae, sediment, denitrification. All the processes you can think of are in the model. Some of the models are much more simple. The same system with the physics. You can build some really simple test case. So we use that a lot. This is just a straight river opening out into the ocean. We use that to study when we have river lows, with the nutrients being dumped or sediment being dumped from the river into the ocean, the impact of that has on carbon and nitrogen cycles in the ocean. So you don't need to build a complex model to study that. You can really do a really simple test case. This is just another model well known in the field, which is the one from the east coast of the US, where it's a quite complicated data assimilation model. There's another one, complicated grid model domain here. This is Moreton Bay, Brisbane here. So you can see we'll talk a bit more about that one. This is the Tasmanian version. This is actually, somebody can guess what that is. This is actually just next door. This is the Darwin model. So we have a model of the Darwin River that goes really fine scale resolution in the 50 meters because we want to do the same thing. There's a lot of sewage treatment plant along the river, a storm drain. We want to understand how the impact that has on the river. Plus, we know it's one of the most polluted estuary in the world because there's now a lot of, notchy metals in the sediment in the Darwin River. So we want to track that and understand what's going to happen to that. So we have a pretty fine scale model. This is what we call the E-Reef model, which is one of the big projects I'm working on. This is just for the whole of the Great Barrier Reef shelf. And the small model we just built is actually nested just built 5 minutes ago. Is actually built inside that one. And this is another one of my baby. This is one of the coral reef atolls. So this is just a model of a Aran Island reef. This is just 10 kilometers. So this is just a model of the circulation inside a coral reef. So it's really diverse. There's a lot of things to choose from. So I must say we can spend 2 weeks talking about those things, but we're not. So we like to, BGC modelers, like to do everything. So you can do everything. There's a relationship and model to simulate everything in the world. From, as I said, the zooxanthellae here inside a coral polyp to, diatoms, seagrass, epiphytes, not Nemo. We don't do fish and ecosystem yet. You can do the, Trichodesmium, you can do zooplankton, you can do corals, you can do a lot of things. This is just, sometimes we like to do everything. But usually everything goes with everywhere. If you do corals, you need a corals reef. If you do muddy and murky waters, you need rivers with murky and muddy water. So that's again to get the signals that BGC has to go with the physics element. So while we'll have to do everything everywhere, we're bound by some rules. One and foremost, computers are big, they're getting better at the time every day we advance, but we're bound by this, you all saw that diagram point, time goes with space, okay? So if you want to resolve, for example, phytoplankton migration, you need to have a model that goes down to hundreds of meters resolution, all right? And with that, it's really expensive, computer cost increases length to time. So it gets bigger and bigger every time you exponential. So each time you add something, you go lower in resolution, you increase your computer needs by a huge amount, which limits yourself. So I've been in the field for 10 years. The model I was using 10 years ago were NPZD style in a 1D box. The model I'm using now, you think they'll be faster. Well, now they're slower because we haven't made the model faster because they get more complicated. So it's always this trade-off between complexity and trade-off as can we run the model. You'll see the small thing we're running now. It's a 3D model. It's going to take an hour to do 5 days. So it's not really efficient. And we're also getting to the state where we have models that run near real time, which means they run as slow as reality because they get so fine, so nested resolution, so many grid points that they run slow. Anyway, so we like to do everything everywhere, but we can't. So we have to be a bit more intelligent than that and build the model for the specific question. So the outline of the talk today is going to brief introduction. So I'll see if I'll go to the math or not. Maybe not. It's morning. Sometimes I'm not into the math, but we'll see. And then I'll give you 3 examples. And if I'm too slow or too fast, I get a 4th example, or we skip the last one if I go above the hour. The first example is, we had this question, everybody knows the Kerguelen Plateau in the Cézanne Ocean. It's a small French island. There's a big bloom of chlorophyll that happens every year in that region. And it's been proven that it's just injection of iron on the plateau. The question is that bloom extend for a lot more than the plateau, 900 kilometers. So the question is the extension of that bloom in the Southern Ocean is due to just advection, or is it just to other processes that bring iron outside the plateau? And all of that is because we want to save the penguins, okay? The second example is ocean acidification is really a hot topic at the moment, especially in Australia with the Great Barrier Reef. We know the reef is pretty much, doomed, but we want to understand a bit more. And I mean, this is not as simple as that. The Great Barrier Reef is 2,000 kilometers. It's a complex system. It's not just one reef is going to be like the other reef. So there's a lot of interplay and feedback between the reef himself. So we have this big project to try to look at that, and we just submitted a paper recently about that. So we want to know pretty much what's controlled the variability that we observe. Because if you want the variability you observe on the Great Barrier Reef in terms of different BGC tracer, pH, nutrients, is bigger than what's forecasted in the next century. So the story is not just, there is going to be that in 50 years. Yeah, that's not as simple as that. So, and again, that's to save, Nemo. And the last one is how to determine how much nutrient you can dump in a river so we don't kill the ecosystem. So I thought about the Derwent, but I'm not in charge of the Derwent project. I've worked into the Moreton Bay. So Moreton Bay is a big bay out of Brisbane. Brisbane is a big growing city. There's a lot of rivers, a lot of sewage treatment plant, a lot of nutrients get dumped, and each city council is fighting with each other. No, my river is clean. No, my river is clean. So we build a big project to say, no, your river is clean, but you're the one who's got the most impact on the system. So, and again, that's to save the turtles in Moreton Bay. So how we do it? So that's the slides before the math. So every single model starts with met forcing, wind, solar radiation. That's the basics of how circulation works in the ocean, okay? So you give the wind, you're pretty much going to bomb website, get the forcing. So forcing, I call that pretty much meteorological forcing, wind speed, solar radiation. That's the basics of how to drive your whole physics. You stick that into some, hydrodynamic equation. This is not a winter school about hydrodynamics, so I won't go into the details. But pretty much with that, you can calculate temperature, salinity, sea surface height, and velocity inside a grid. So that's the trick here. You have to discretize, decide how much I need to build that grid. And the trick here is to do that. I mean, we showed the example that was really simple when we did it on the web like that. But we built something really simple. When we start to get those kind of curvilinear funky looking grid cell, it starts to get complicated. There's a lot of numerics, a lot of problems. That's the trick. That's the hard part of the modeling, building BGC modeling with physics. The physical oceanographer, physical model, they always want to get the finest, the best looking grid, but that makes the model really slow. And whereas BGC will always fight back, say, now, I don't want that 50 meters resolution in that river because I'm not interested in that region. So it's always a fight, not a fight, but just interesting discussion we have with hydrodynamic modelers. Anyway, so you do that, discretize, because I'm coastal shelf modelers, I don't do global models. So one problem we have when you build those grids is what you do here. You don't actually do anything in here. So you have to, what we call nest. So you nest your model into another model, another model, another model, until you actually get to the global scale model. So that's the nesting part of it. And there's also a lot of trick problems, that's numerics that you get when you do that. The physics is a lot more advanced than we are, the hydrodynamics. The BGC is a lot more complicated, but I won't go into the details. So when you have that, you stuck your BGC model or biological pump, and you get those equations, which is the variation, derivative of your tracer. It could be nitrogen, could be phytoplankton with T, X, Y, and Z. So in a kind of 4D with 3D with the time is the source and sink from your biology. So that's your NPZD model that you guys have, growth minus mortality, plus all the physics term. And that's pretty much what you do. You run your NPZD in every single of those cells in 3D mode. So it's like running your model a lot, and you exchange variable or tracer between those blocks, and the hydrodynamic is doing that. So I'm not sure I'll go to the next slide because we're just going fast, but pretty much models, you said, as my box, and there's a lot of box around it, and you say, flux in, flux out. So the variation of my biomass, the physics, is whatever gets in my box minus what's leaving my box. So that's the theory. So again, the theory is really simple. It's just you have a box. I want to calculate the change of biomass with time. So there's my biology, my phytoplankton does stuff. But then, I get phytoplankton coming from the neighboring box and some phytoplankton leaving the box. So that's the easy part. Then the hydrodynamic gives you a lot of things. Okay, this looks bad. It's actually not that bad. We don't have time to do that. It takes a full hours. But pretty much, you do a bit of geometry, a bit of math, and you come up with this is just because you're in 3D. The world is not. When I came back to that one, I only show you that face to that face. Well, we have 6 faces in a cube, so it's a lot more complicated. So that next equation is only dealing with that. Dealing where the world is not just I'm going one way, there's stuff going around. So this is all the math and geometry and those funky divergent term that gets there. But pretty much we can, if we know how much the flux, and hydrodynamic gives you that, and I know my concentration inside my box, I can derive how much I change my concentration inside my box. So that's this term here, this fancy term. So my variation of biomass, even the volume is doing, so relate mass to concentration to surface area of your grid cell, blah, blah, blah. You can go a lot. Again, I had to do that, so I won't get to the details. If you're interested, there's tons of materials about that. That is a lot well explained. I'll go fast. What I want to, that's the last one. But we want the variation of your concentration with time. That's in your box. That's what you want. And it's related to this, we have a bit of diffusion, because diffusion, occurs in both ways. If you remember back in physics, if you have, velocity currents going that way, well, currents only going one way. Diffusion goes both ways. So that's this term here, this divergence square thing. But that's the most important thing is that divergence thing is here, okay? That's U, V, W. And the hydrodynamic model is calculating that. So we can really relate in those models, after doing a bit of math, U, V, W, diffusivity, you plug the entire equation, and you know how much your biomass change. Okay, I don't want to go more in details. I know I went really fast. We can, again, spend an hour, just a lecture doing that. But the feeling I want to give you is just, usually hydrodynamic guys give us a model, a grid, they calculate U, V, and W, and that's the only thing we need then to actually know how much the biomass changed from one grid cell to another. That's as simple as it gets. And the only thing you have to do, you do that, that's the physics, and you add your source and sinks from the biology. Simple, but it is. All right, so pretty much, if you summarize, BGC tracer are advected and diffuse between one box to another, depending on the gradients they have between, the concentration of the neighboring box and my box, and the rate at which the exchange occurs, which is given by the hydrodynamic model. So in a sense, it's not that much different than you guys, I think, had to look at box model. It's pretty much the same system, a bit more complicated because there's numerics and there's 3D and there's a lot of different things, mass conservation, blah, 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 blah. As BGC modeler, thankfully, we're only in charge of the sourcing term at the end. So we had the easy part, but not all the time. So sorry about the quality of the thing. The thing I want to show you here is most of the code. People are always scared to go inside the BGC or MUM for RUMS, any of the model's code. And actually, if you look at them, they're actually quite separated. Like in the model I'm using at the moment, this is the kind of code I'm dealing with. This is just showing you, this is a sourcing term. So everything I do every day, I never look at the hydrodynamic. Okay, the hydrodynamic is done somewhere else in the code. In the code, I have just an equation. This is just the renormalization. There's a few things. This is C++ or something. But anyway, you get just sourcing of my biology. I don't have those fancy divergent term in my model. It is dealt somewhere else. So you don't have to understand or know the whole physical advection thing to understand how the system works. You can just go and edit that, and don't be scared of doing it. The codes are not that bad. They're just plain English sometimes with a bit more thing. But I really push so people just should go and open the code because people are scared sometimes. It gets complicated, but they're not that bad. You just have to read them backwards sometimes, but it's not that bad. I think the difficulty in the whole BGC world, it's not the code, that's the geeking around. It's not the physics, it's well known. It's how to deal with the sheer size of those models. So, for example, here, in the model I'm using, the complex one, this is when you use the user guide of the model. The first page, you get equation. This is just for the Biogeochemistry, okay? There's no physics in there. The first equation is number 1. The last equation is number 219. So that's the difficulty. That's, that's the hard part. The easy part, the physics and stuff, that's easy. That's the hard part, okay? That's it looks simple here. Look, oh, it's just big NPZD model. Well, each time you add a tracer, you multiply things by an order of magnitude. So we have 200 equations. Okay, it depends how you discretize the equation. Some of the equations are split into more than one. But to give you a shot, that's the challenge. The challenge is the equation. And the number of grid cells we saw as because the hydrodynamic guys wants to build the biggest grid ever. So you have a lot of grid cells, a lot of variables, a lot of equations. So that's my life. That's the hard part, is to deal with that. That's the difficulty, not the code and not the theory and not the physics. For example, in the 1 kilometers model of the Great Barrier Reef, so the grid size is 2,000 by 500 by 47, so that's longitude, the latitude, longitude, depth. We have 100 tracer in here, so it looks simple as 100 tracer. I didn't do the math, but that's a lot. Okay, and that means it's big files, big computing files. So it's heavy to manage. Just the day-to-day management is difficult. So that's the trick. And that's when I go back to say, if you take a model and don't use the model fit for purpose, you're going to end up with a beast like that to do something really simple. You're going to lose a lot of time, waving stuff in the air. So which goes back to the first example. Okay, let's try to save the penguins in the Kerguelen Plateau. So the problem, this is just, a satellite view of the Kerguelen Plateau in the Southern Ocean. So this is Antarctica. This is Australia, small island here, Heard Island, Australia. This is France, bigger. And so this is the only boundary between the two. Anyway, there's a lot of fishing, a lot of money, a lot of things happening there. And you can see there's a view. This is just a climatology of chlorophyll. I don't remember how long, but this is just a few years of means of chlorophyll. You can see chlorophyll. There's a big bloom. It's a big bloom. Okay, and outside there's nothing. Guess what? In here there's a lot of fisheries activity, a lot of money involved. So we want to understand what's controlling that bloom. Why do we have a big bloom of chlorophyll? And so there's been a few campaigns too, where the frogs have been at sea in there from Kerguelen. They go and measure iron, okay? And they realize that the red one is on the plateau, the blue one is outside the plateau. The plateau is pretty much, sorry, I didn't define the plateau, we can see the bathymetry in the back here. Pretty much they say, well, this bloom here on the plateau is due to an injection of iron, which is a nutrients, and it's limiting. So as soon as you put nutrients, phytoplankton is really happy and grows, like, oh, it can do a bloom. Outside, there's no iron. So they say it's an iron-fertilized system. Great. So you can explain what happens on the plateau. Well, again, those are the red dots they did on the cruise. Well, the question is, what happens to that one? That big bloom here, what's controlling that? This is the same story. It's just this bloom getting advected around. Well, you're not going to go on a boat and do that. You know, it's too expensive. Again, we can't measure everything, and satellite only sees the surface. So the question we have is what's controlling that? If you look in more details, you know, you can try to look at satellite. You say, I can look at satellite image from day to day and can track how big the bloom gets and get, well, the problem with satellite, there's bloom. So this is only the 8 good image you get for 3 months. So you only have 8 images clear without cloud for 3 months. So you can't use satellite to track your bloom. You can't. So let's solve that problem. So the question is, you know, the extent of phytoplankton bloom, it's 900 kilometers down to Michaelian Plateau. We know there's, you know, iron from the plateau. The question is, what's controlling it? So we're going to use a model. All right? Well, we don't have to use a complicated model to do that. Okay? We don't need to get the polyp and those antilli interaction to understand what's going on here. So even the physics can be quite simple. So we're only going to do a simple model to see if we can reproduce the plume of chlorophyll. So one trick we do before is we want to be sure that the bloom, and we looked at a lot of remote sensing image, happens really fast, because people will say that's just the bloom growing, you know, forget about the advection. So we went and did a lot of work and say that, you know, the big change occurs within a few weeks, okay? So it's not just the advection of chlorophyll itself. That's what we want to get at. You know, we can say, oh, it's just that chlorophyll gets advected, okay? Well, change occurs way too fast. So this is not just the chlorophyll that gets advected. But you can't prove the point. You can just get a feel that it's not yet. You know, we're scientific. We like to prove the point. So we build a really simple model. And that simple model is just, you know, 900 kilometers. Okay, just 2D. This is a MATLAB code. This is really simple, you know. You know, just 2D. We don't even do syncing or mixing. Simple. What we're going to do, we're going to inject in that system here tracer. We're going to say this is the plateau, okay? And I'm going to continuously release something in that plateau, you know, which is iron, and see if that gets advected further out. So as I said, we even use, you know, we don't use any met forcing. We don't even have a physical model. We're going to use, you know, geostrophy because it's large scale. We don't even need, you know, we can use just pure geostrophy in a 2D model. So we use altimetry to derive the velocity. So ultimately give you how much the ocean goes up and down, and can derive the velocity from that. And we release a tracer along that plateau, and we assume that's, you know, it's iron. And we assume it has a really simple dynamic, which is going to make, you know, people who look at iron really scared. We say, you know, pretty much you have a small decay. Your iron, you get advected around, and you're slowly kind of sinking out. So the equation for the whole tracer is really simple. This is the thing we saw before. There's no W because it's only in 2D. We don't even deal with the sinking. And we have this lost, and this is my BGC model. Doesn't get any simpler than that. Just simple. But simple can be really powerful sometimes. And so here's what we get, okay? Bit of movie. Okay, so you release, you get advected. Eventually you're going to reach a steady state because remember, you get a constant source from here, but at the same time, if you're here, you lose a bit of your biomass every time with this lambda term. So you're going to eventually after a while reach a steady state, which means you develop this kind of plume, and it's not going to move. It's going to move around because the velocity moves, but it's not going to go much further. So you can see the point now. Now we're going to go back and compare with the real world. Well, so now we reach a steady state. You're not going to get much further. Forget about that. This is an artifact of the model. But you can see, there you go. Here's my plume, reaching a steady state. I'm all happy. I can now derive and do some good science. We can, now because we submitted this published paper, we had to prove that our advection system worked. Okay, so I'm going to bypass that slide. But we had to prove that our velocity were good enough. So we had to compare with observation. There you go. So the green, which is the snapshot from the top. The green is the control of chlorophyll from remote sensing, just a huge climatology, just take a 3 or 4 months mean. And the red in the back is my tracer, okay? And this lambda, I have no idea what lambda is. Lambda is summarizing all the iron dynamic, NPZ, everything. So I have no idea what lambda is. We can't measure lambda. This is just a decay rate. So we did a few sensitivity analysis to say, if I have lambda 1.5 per day or 0.4 per day, how does my bloom spread, okay? If you get a smaller lambda, the bloom goes further away. So you have to kind of calibrate your model, which we did in that one. So we decided 1.5. Again, we did some statistics to do that, which I'm going to pass around. We did some statistics in which decay rate should I use, so I can just have the best coloration possible with the actually observed extension of that chlorophyll plume. So we did that. So we kind of build my model, I calibrate my model, but so far I've done nothing. I just reproduce reality. Well, with a simple model, not that exciting. The exciting part comes with that. In 2004, the bloom was quite big, okay? Big bloom. 2003, sorry. 2004, bloom was quite tiny. All right, if I run my model with the real velocity from 2003 and 2004, what happens? Oh, guess what? 2003, I got a big bloom with my model. 2004, I got a small bloom with my model. Well, I proved a point. I just proved that advection, or velocity, is controlling the extent of your bloom from one year to another, which means in the back it does control this bloom. Okay, this is one question, one answer. Okay, the story is probably more complicated than that. But we just prove that what's controlling the extension of that bloom is a tracer from the Kerguelen plateau, and it's not chlorophyll, it's just iron. The mechanism behind it: in winter, iron gets ejected, it gets slowly advected around. Summer comes, light, poof, you have a bloom. So that's the simple mechanism. Okay. Since then, there's been a second campaign when people are going to go and try to verify that hypothesis. But that was just a simple question. You build a simple model to answer that question. So the take-home message is, we had a simple model to answer the questions. We use the model best suited to answer the question, not the biggest, more complicated model. All right. Now we're going to go the other way around. Okay. Now if you have a complex question, try to save Nemo. That's a lot more complicated. The Great Barrier Reef is complicated, beautiful. Ocean acidification, I don't know how you were, but as we drive our SUV in a street, we dump more CO2. CO2 goes in the ocean, produce ocean acidification. So that's as simple as it gets, and this is just the equilibrium of pH. As you put more CO2 in the system, you change everything, and you have ocean acidification. Well, who cares? Ocean acidification, I don't care. It's not going to be like, as acidic as, Coke or something. So I can still go through where calcifying organisms do care because they try to build calcium carbonate. And calcium carbonate can't be built when pH is too low. So we define, because, we BGC and biologists, we like to make things complicated when they're simple. So we derived as what we call aragonite saturation state. Well, aragonite saturation state is actually only the concentration of calcium carbide ion, okay? But it's historical, blah, blah, blah. It's practical to use. It varies between 0 and 5. It's a nice number to deal with. Pretty much it's like, no, I shouldn't say that, but it's like pH. It's just a proxy for see how acidic is the ocean, or more, how easy is it to build a calcium carbonate shell. That's the thing. The most important thing in models, or in people even don't do, even people who measure stuff, we can't measure aragonite saturation. What you do, you measure DIC and alkalinity, temperature, and salinity, and then you can derive from those four what aragonite saturation is. There's a book that thick that does that. It's the carbon chemistry. Anyway, in models, you can see that if you change the concentration of DIC in the ocean, and what changed DIC in the ocean? Phytoplanktons or plankton, a lot of things happen, so you change your carbon. It's solid inorganic carbon in the BGC model. What changed alkalinity? That's a more tricky. That's calcification, that's change alkalinity. Freshwater, that's change alkalinity. There's a few other processes, so maybe people are usually not that aware of what alkalinity is. But pretty much, BGC does change those two parameters in the world, and that's what we try to do. The question we have is, big people, IPCC people say, the reef is dead. So they use, global model with NPZD. Well, how do you think a global model at, 25 kilometers resolution, horizontal, and the NPZD model is representative of what happens in the GBR? Well, okay, but the point, the model was not designed for that. It was designed to answer the global scale problem. So, they get the GBR here, and they try, look at the GBR. Well, it's just dots. You don't resolve the system. Here's your number of reef with how much aragonite varies. Well, you don't really resolve anything. But again, that was not the purpose of the model. And I built another model, this one. Ooh, really nice. Reef, 10 kilometers, really cool. Well, same problem. This one was designed to study what happens inside a coral reef on the diurnal cycle. The impact of the tide flushing the lagoon, the fact that, you have respiration at night, you have dissolution and calcification during the night and day. So that was just to look at a really diurnal cycle, what happens inside a coral reef, okay? That was that model. Well, in that top model, the aragonite saturation varies between PCO2 in the atmosphere, okay? That's pretty much what's driving it, and global scale weather. Well, it's not going to help us to decide what's happening to the GBR. And on a small, really fine scale model, it's all about the really fine scale reef processes between the lagoon here. This is just, sorry, a map of aragonite saturation. You can see there's a lot of fine structure inside the lagoon. This is just 10 kilometers. So that variability here is controlled by local reef processes, the residence time of the lagoon, how you get flush with the tide, and synoptic weather. And synoptic means, when the fronts come through, like, we have today and things like that. So this is really fine scale. This is big scale. Well, the GBR is 2,000 kilometers. So what's controlling the thing in the GBR? Well, we can't use any of those two models to derive that. They're not fit for purpose. So we have to build something else. And so that's what we did, okay? And even if we like to send students to measure argonauts and DIC and alkalinity on individual coral reef, I think any of you would love to do that. Well, there's, 4,000 reef. So it's going to take a long time. And you get a lot seasick. And it's actually not that nice. So there's the GBR. So, and it's a complex system. There's a lot of blue water, boring. There's a lot of really nice, cool picture, really cool. And there's a lot of murky river. So you can see what I'm coming here. This is a really complex system. So you're going to need a really complicated hydrodynamic model, which we have, okay? So that's the global model, 4 kilometers model, down to 1 kilometers model, down to the small model we just built at the start. And you need the KICAS BGC model that does everything, because the reef, there's everything on the coral reef. There's, phytoplankton, dinoflagellate, trichodesmium for nitrogen fixation. We need the carbon chemistry, obviously, We need sediment, because you can see the river that you showed just full of sediment, so you need the sediment diogenes thing. You need, macroalgae, epiphytes, you need seagrass, you need corals. You need the whole lot, because you have the question. And so when we build that model, that's what we get. This is just the 4K model, so this is just the hydrodynamic. You can see circulation is complex, that's the GBR lagoon in here. You can see here, what we want to get at is just, you can see, this is the lagoon, this is the reef. You can see here, velocity really high, really shallow on the reef. So tide just zoom through. So you get high velocity here. This is due to the tide. And this is just the phytoplankton in the model. Again, you have, a lot of structure. You can see uppooling along the continental shelf. Well, it's a mess. It's a complicated model, complicated system. There's 10 people working full-time to deal with that baby, so it's just not my effort. It's 10 people working on it. What you get, seagrass in Moreton Bay, you get calcification in the outer reef, you get nitrogen fixation in the lagoon, you get, for example, this is a river, you get oxygen drawdown when the river comes down, you have oxygen sinking because current pollution is high, you get, attenuation of the light due to those sediments that you saw. There's benthic macroalgae out of Mackay, and there's a shelf break chlorophyll maximum. This is just a section. You can see you have a deep maximum chlorophyll in the offshore water with this bloom at the shelf because water push and brings nutrients up. So we need to resolve all of that to decide what's happening to my DIC and my alkalinity for the lagoon. So this is the result. So forget about the left panel here. We're going to focus on that one. So when we run that model, we steer the pot. I can't speak for 2 hours just about that paper, so I went a bit fast, sorry. Very much what we did here, we can calculate my aragonite saturation in the model, and more than calculating for the whole model domain, which we want to do, say, oh, look, my model is big, I can shoot aragonite saturation at every kilometers for the whole of GBR. Well, no, the question is, what's aragonite saturation on the reef? So only show aragonite saturation on the reef. Who cares about aragonite saturation in here? I don't care, there's no reef there. So the trick was to really only show what you need, and that does change completely the view. Because if you plot the whole thing, you're going to see here only the rivers or the open ocean, you're going to kind of miss the point. The point is the reef. So that's what we did here. And this is just not the value of aragonite saturation, this is the variability from the mean state of the global open ocean. So this is what the value are here. But you can see here, you have gradients. You pretty much are usually lower inshore and higher offshore than the global mean from those SkyPCC kind of people. And you also have north to south gradient. Well, this is a big picture. This is not one reef doesn't have one value, okay? And that means if you go forward in time and increase PCO2 in the atmosphere and say one reef does it all, well, when you look at that picture, I will say, no, it doesn't, okay? This is the reef you want to visit last, okay? Those one are doomed. Go and visit those one. They'll be the last one to kind of disappear. Because what happens if you have actually upwelling on the shelf that just do things. So this is just all the introduction of BGC. So again, we can go further than that. Oh, sorry. We can actually use observation. So, well, if you send students on those Mercury River and Reef, this is the only observation we have for organized saturation for the time period we have. It's not a lot. And you can see those two figures are quite different. Guess what? We can't go on the reef. There's a few coral reefs you can go and sample. So they're just not accessible. So again, we need models to do that. All right, so organic saturation, go back to it. So biological pump does influence phytoplankton growing and dying, does influence organization through DIC. And because we have a model, we control everything we do in the model. So I can actually isolate that term. And I call it PRA, photosynthesis, respiration, and gas exchange. I can isolate that. In the variability you saw, I can say, oh, that's only, I can know the percentage of the variability due to photosynthesis and the biological carbon pump. Well, I can do the same with the solubility pump. I can do the same with the freshwater, just change the salinity. So pretty much when you have freshwater rivers being dumped in the ocean, alkalinity is usually lower than the ocean. So that's kind of a sink for alkalinity. So I can calculate that because I got a model. And I know what my reef is doing. I know what's the calcification. I know what's the dissolution and photosynthesis and respiration of my reef that change CO2 and alkalinity. So I can, again, put that into a MATLAB script, get to a few equations. Again, they're quite simple, but I won't get into the details. You get to that map. So I can actually extract the variability. So I can say, okay, in that point up north, I can see now which BGC process is responsible for that variability. In behind, I can really start to understand and get the big picture, who's controlling what and what's controlling who. So here I can say freshwater, tiny. Okay, those numbers really small. If you talk to stakeholders along the Great Barrier Reef, they say, oh, we should stop dumping nutrients in that river. It's really important. Like, well, rivers are really not a trivial. Guess what? Coral reefs just don't grow in the mouth of a river. Okay, so you can forget the whole freshwater input thing for the reef. At that scale we're looking at, not that important. Well, calcification dissolution is important. Okay, what I want to get is not the calcification dissolution of the reef you're in. It's the calcification dissolution that occurs on the reef next to it. Because what happens? Weather does move. And so, well, people say you're on a reef, you flush the water with open water. Well, you don't really flush it. You don't reset the system. You reset the system with water that already has a signal. Okay, just because water moves around, there's tide, it's complex circulation. So it's really processes that occur upstream of where you are that controlling you. And that's really what shows in that picture. What happens here, for example, this is photosynthesis respiration here, because you are the outer reef, those upwelling that push and create a bloom just on a shelf break, they do change GIC alkalinity in that regard. But this is just the bloom doesn't happen on the reef. It happens just outside the reef, but it gets advected. And so that's the whole integration. So we use the mold to integrate that. Another way to make the picture be clear is that one, okay? So again, that's the first figure. This is the difference with the mean ocean. This is the different drive. If you do the sum of those three, you get to that. And in the back here is the world. I say, hey, what happens if there's no physics, there's no hydrodynamic, there's no currents? I know how much calcification and dissolution and stuff I have on my reef. What happens? You get that picture here, okay? Look at the scale. That's, going to 0.1 to -1. Here we get 0.8 to 0.8. That means I'm really reinforcing the problem that it's really what's happened upstream. This is if you're on local process, what happens locally. Well, that's not valid. You need to integrate with how it happens around yourself. I mean, it looks, for some people, say, well, that's normal. Okay, but you can't do that without a model because we don't know what's the circuit. You need to integrate the whole thing in the model to understand how the system works. And that's this whole integration kind of story. So that was the big complicated model, okay? Again, we developed the model that fit the questions. Yes?
How do you separate the local variability of your variable there?
All right, so what we do, we know in my grid cell what those sourcing terms are. Remember in the equation I showed there's a physics that moves stuff around. You know what's changing stuff on my reef. So you know how much you change GSE per hour locally. Yes, but you have a model, you can separate those two. That's the whole point of the model. So this is not truth, this thing here. This is just to show that if you were to stop this, it's just to give in people's head that what happens, you need the circulation, okay? The circulation is really important. But some people, obviously you know that, but some people don't. Some people will say, my reef gets reset to 0 every day, so only what happens on my reef is important. I don't really care what's next door. Well, it is important what happens next door. I mean, I know for some people it will look really simple, but for some other it's not. And usually the way it's been done for the reef community, because the system is so big, as I say, people used to go with a few students on a boat measuring stuff. Well, it's really hard. You can't just do that for all the reef around you. It's impossible. So you need the model. So you need to change the way people think and the way people approach that problem. So that's how, I know, I went a bit fast. This is just an hour talk just by itself.
I just want to understand what your local variability means.
Yes, it's just a local thing, yeah. All right, conclusion. Develop a model again to fit the purpose. Well, for once, we used the model best suited to answer the question. We didn't use the smallest and the less complicated one. We had to use the biggest and most complicated model to answer that question. So we did. All right. Plus the trick here, and I think it's a really take-home message for some of you, is to only show what you need to show. You don't have to show the world, only show what's needed, because it does change completely the perspective you have to the results. Because again, if I show that map of aragonite saturation goes to 0.5 at the Mathieu River. So the color bar will just change completely, shade what happens on the reef. And people, when they look at it, they'll go, oh, look, aragonite is really low at the Mathieu River. Reef don't grow at the Mathieu River, so we don't care. So that's really important to get that vision in modeling in general. All right, quick, last time? Yes, 10 minutes, we can do that. Okay, save the turtles in Moreton Bay. So that's another project we have. I must say, the first two projects are really fun. This is a lot more complicated because this is to deal with stakeholders and real people. We only deal with the reef and Nemo and things. This is to deal with local people, farmers and stuff. This is going on sidetrack of the politics, but models are used for that too. So this is Moreton Bay. So all those things here, there's a lot of people in Brisbane. This is all the sewage treatment plant. Ooh, a lot of them, around 50. Dumping stuff in the rivers, okay? Or they try to clean them, but there's still not zero release, okay? Some of them are not always tertiary. They do release nutrients in the system. And there's a lot of river, I think there's, depending on the count, between 12 rivers, more or less, in the system. Again, dumping a lot of nutrients, a lot of, because there's a lot of farming, sugarcane things happening in the back of Brisbane. Not sugarcane, what's happening? No, other stuff. Anyway, it's complicated. There's a lot of nutrients being dumped. And to trust me, this is what Moreton Bay can look after a flood. So it does look filthy. Okay. The problem is it's a really interesting system. There's definitely no turtle in the Brisbane River, for those of you who have seen the Brisbane River. But there's definitely turtles on the other side of Moreton Island. This is here a beautiful place. There's seagrass, there's dugong, there's range of wildlife. It is beautiful. So there's a kind of a strong gradient across. So we don't want to stuff that up. So we need to control really finely how much nutrients we can or should release in systems so we don't kill everything. Plus the system is prone to flooding. So it's not just a continuous flow. It was a continuous flow, it will be easy. I mean, things happen. Sometimes there's no water for a month in Brisbane, and then all of a sudden they get water up to their roof. So it is not a simple system. So again, we have to build a model. So for that, sorry, I should have blocked that one. We use the same complicated model, but we just kind of don't need the corals. We didn't do the carbon chemistry. There's a few things we just switch off. Sorry, this is the wrong slide. We switch a few processes. We're only interested in nutrient impact on biology. We don't have turtles in the model. I'm just kidding when I say we have turtles. And we build a regional grid, but we have quite fun resolution inside Moreton Bay in terms of the hydrodynamic, because we need to resolve the different plume of water exiting Moreton Bay. And for those of you who have been in Moreton, this down there, it's beautiful. It's really complicated, like channels, shallow. It is a mess. It is such a mess. Even the model tried to see how curvy the river is. So that's the point I was getting to the hydrodynamic guy. I said, why don't you build a straight river? It makes my life easy. I say, no, it's really important because when the wind blows that way or that way, the water moves differently. They get to those kind of details. But guess what? What happens when you have this, kind of convoluted grid, makes everything a bit really complicated. In that specific grid problem is what are pushing sediment, and sediment, because it's still a box. Okay, this is not the real world. So sediment were just accumulating in that box, and the whole model crashed, and then we had to fight with the hydrodynamic guys, say, can you build something a bit simpler? And anyway, this is, I go back, the difficult part, the communication with people. Anyway, so we run the model, okay? With all the river, we know all the data, we have to fetch the data that in the river, nutrient concentration in the sewage treatment plant, blah, blah. Anyway, to make things simple, I just subdivide the whole model into different regions. And those regions, I didn't decide. They're actually city council region, okay? I didn't decide. This is Deception Bay, this is my territory, so you have to show me what happens in Deception Bay. I don't care what happens next door. This is politics. You have to deal with it. You put nutrient load in the region, so that's the nutrient. So this is just, I think, this is a season. This is just, this is 4 years. So you can see sometimes there's no, DIN loads in the river, and sometimes there is. So it's quite a variable system. And then you can see the ecosystem response. Okay, so you can see when you, dump nitrate in a river, oh, you have a bloom. Cool. But behind that slide, we want to show that, we don't want to calibrate the model. I won't touch on that. But pretty much, you want to do that slide to say, oh, cool, my model is responding correctly to what we expect, okay? I have a bloom because I dumped nitrate. It looks simple, but it's not always that simple. You want to get the right magnitude of your bloom. All right, so we have seagrass too. So in that model, usually we impose where the seagrass grow. In that specific model, we want to let where they actually let them grow naturally, because that's the whole point of the project. Say where we're going to start to kill the seagrass and start to kill the ecosystem. So again, observation model. We're happy it does, what it does. All right, so now we can say, look at small stuff. Okay, what happens normally? Okay, that's just simulating reality. What happens? Okay, so this is just nitrate out of the Brisbane River. So, oh, there's a flood, nitrate gets away. Well, you didn't learn much. Again, we did just what happened. We simulate what happens. Didn't learn anything. Okay, the interesting part, and you can do the same with the chlorophyll. All right. Now it can be tricky. Say, what happens in Brisbane in 50 years? Okay, if I don't change anything. Sorry, I just got lost there. Right, so I go back, sorry. So that's simulating the reality. We do the same with the chlorophyll. You can show a nice movie, you get a bloom where you have nitrate. Again, you didn't learn much from here. The interesting point, it doesn't get there, okay, where you have all the turtles and nice ecosystem. So that's the trick. Okay, just to show off a bit, there's a lot of structured happenings. That's just justify the fact that we go 3D and not 2D. Remember model complexity, why didn't do a 2D model? Well, because even if it's really shallow system, you do have subsurface happening, in the 4 to 6 minutes. So you do have to resolve the subsurface, so you need to go 3D. All right, so now let's do the interesting part. Don't look at those numbers. I'm not allowed to show the number, okay? So those are just test case. So we use extreme scenario. That's what we can do is say, okay, let's imagine, that's the baseline. That's just, if nothing changed. That's if the nutrients increase by factor 5. That means if, we don't do anything to clean up the rivers. And that's if we start to be green in Queensland and divide everything by 10. Okay, so we can run the model by adjusting the nutrient input in that system and see what's the response. Oh, look, okay, maximum chlorophyll scenario. If you don't do anything and the river gets 5 times more dirty, ooh, chlorophyll bloom everywhere, naughty, bad. Even outside, ooh, bad, ooh, that looks really poor turtles, okay? What happens if we try to get your act together? Oh, look. It's actually quite a clean system. Still a clean system. Nice. All right? Well, we can do more than that. We can actually start to zoom and understand the system. So this is kind of baseline. This is the same thing, but just zoom in on the model. I'll show you the model is really high resolution. So again, you have to zoom into the different region. So that's the base scenario. That's the Brisbane River. The airport is just there. That's just normal condition. That's what happens when,